In this video, I want to discuss and compare the difference of squares factorization with the sum of squares factorization and work a few examples. So we see that the difference of squares factorization is a plus b, and then we have another quantity, a minus b. Your sum of squares factorization looks an awful lot like the difference of squares with one major addition. We have these i's right here. So what happens is that these quantities end up being complex in nature. It's because the I is the square root of -1. And we have to have that in order to get this plus right here. All right, so let's look at a couple of examples. We'll first compare x squared minus 36 and x squared plus 36. We know that x squared obviously is a perfect square, and 36 is also a perfect square. So the square root of x squared is just x. So we'll place those quantities here and here. And we're subtracting, so this will be the difference of two perfect squares. So we have one addition and one subtraction. And again, the order that you put those in doesn't matter. This one could just as easily be subtraction, and this one could just as easily be addition. And then the square root of 36 will be 6. So our b value then goes last. So x plus 6 times quantity x minus 6. And of course, when you multiply this back out, you'll see that the x times the x makes x squared. X times -6 makes -6x. And when you distribute through the positive 6, you'll get plus 6x and minus 36. So the key here is that these middle terms end up canceling out because one is -6x and one is positive 6x. So we know this factorization is correct. Okay, so how does that compare then with the sum of squares? Well, using the formula, we have the sum, because it's addition. It's going to have all the same pieces, a plus b and a minus b, but the second term will have an I with it. So it should look something like this, x plus 6i and x minus 6i. Okay, well, how does this I cause this to be positive, and why does it work out? Well, let's go ahead and distribute through. So x times x is x squared, and then x times -6i will be negative 6ix. And then we'll go through here and positive 6ix. And then 6i times -6i is negative 36i squared. And here is the key. This I squared is actually a -1, so it causes this subtraction sign to become an addition sign. And that's the key. Notice still that these middle terms cancel out, so now we're left with x squared plus 36. So there's the difference. So when you're subtracting two perfect squares, you'll end up using this formula, and it'll look something like this. When you're adding two perfect squares, it will not factor over the real numbers. You'll have to use complex numbers, and you can use this formula, a plus bi and a minus bi. In this example, we're going to look to factor this binomial expression as much as possible. So we have 6y to the 6th minus 6y squared. So first of all, I notice they have a greatest common factor that I can factor out of both of these terms. And it looks like 6 and y squared. So when I factor that 6y squared out, I'm left with y to the 4th minus 1. Well, the y to the 4th minus 1 looks like it's difference of squares. So remember, difference of squares, a squared minus b squared can be factored into a plus b and a minus b. So we just need the square root of both of these terms. So the square root of y to the 4th is y squared, and the square root of 1 is 1. So y squared minus 1 and y squared plus 1. And remember the order that we put these, the minus and the plus minus, it doesn't matter because multiplication is commutative anyway, so it doesn't matter the order that we put those terms. So y squared minus 1, I notice, can also factor down, and that's another difference of squares. Similarly, my y squared plus 1 can factor over complex numbers because it looks like it's going to be the sum of two squares. And that formula was a plus bi and a minus bi. Okay, so we can go ahead and use both of these formulas. So we have our greatest common factor, which was 6y squared. So now y squared minus 1, we need the square root of both terms. So the square root of y squared is y, and the square root of 1 is 1. So y minus 1 and y plus 1. And our y squared plus 1 sum of squares will factor down very similar. So the square root here is y, but the square root of 1 is 1, but we have to put an I with it, so 1i, so I'll just put I, and then y minus I. So this will be the full factorization, taking into account complex numbers as well, for the initial binomial expression, 6y to the 6th minus 6y squared. So always be careful that when you're doing difference of squares, sometimes you can have more difference of squares or even sum of squares kind of hidden inside here. So just because we get this first one done, we take the greatest common factor out and then we use difference of squares once, doesn't mean we're done. So always kind of be aware that they could have more hidden factorizations once you do the initial one. So here's the fully factored form for this initial binomial expression. In this last example, I would like to factor this binomial expression. Well, it looks like I have a plus, so based on the video that you're watching right now, probably should be using maybe sum of squares. Well, 49x squared is a perfect square, but 20 is not a perfect square. So can I still use the formula even though 20 is not a perfect square? Well, let's see how it works. So we have a squared plus b squared, and that factored down to a plus bi and a minus bi. Well, to go from a squared to a, we just need the square root of it, right? Well, what's the square root of 20? Although it's not a perfect square, we can still find the square root. So I'll put 20 over here. Let's find the prime factorization. Okay, so I can rewrite this as 2 times 2 times 5. And we have a pair of 2's here, which 2 times 2 is 4, and that's a perfect square. So that'll come out. So the square root of 20 is actually 2 times the square root of 5. Okay, so I can use this. So the square root of this first term, so our a will be 7x. So I'm going to put a 7x here and a 7x here. And then it's plus and minus, so plus and minus. And we'll also need i's in here, so I'm going to go ahead and sneak those i's in right now. And to finish off, our b value then was the square root of 20, which reduces to 2 times the square root of 5. So this will be the factored form using sum of squares. And it's okay that 20 wasn't a perfect square. We can still use this anyway. Let's go ahead and multiply this back out and just kind of show you that it worked out nicely. So the 7x I can distribute, and then the 2 radical 5i I can distribute. So 7x times 7x, 49x squared. 7x times negative 2 radical 5i, okay, lots of terms there. So negative 14 radical 5ix, and then we have a plus 14 radical 5ix, and then minus, so 2 radical 5 times 2 radical 5, 2 times 2 is 4, radical 5 times radical 5 is 5, so 4 times 5 is 20, I squared, and of course I squared is a negative 1, so it'll change this negative to a positive. And these middle terms cancel, which is perfect. So 49x squared plus 20. And we're back to where we started. So we know that this factorization using the sum of squares was correct.